Okay, so good day, Maxite students. Okay, we're moving forward to our second module, which is entitled Parallel and Perpendicular Lines. So we've encountered parallel and perpendicular lines during the first quarter, and we've tried to solve different problems involving parallel and perpendicular line properties that we used, of course, to solve for different values. But in real life, okay, so we can see a lot of applications of these parallel and perpendicular lines. So for example, you have your tree. Okay, so here we have a trunk of a tree, and here's the ground. Okay, so the trunk of the tree, okay, is perpendicular. Okay, it's perpendicular to the ground. Okay, so that means this angle right here measures 90 degrees. Okay, so there you go. So it measures 90 degrees. So that's one example of a perpendicular lines in the real world. And also, if you have looked at buildings, okay, so a building is straight only when it only looks straight. So a building will only look straight to you if all of the angles that's been inlaid for the concrete there is at 90 degrees. Okay, so it cannot look straight if it's 89, 88, 87 degrees. So it always has to be 90 degrees. Okay, so that's one of the important what do you call this, applications of angles. Okay, so our knowledge of angles gives us good buildings, good skyscrapers that we commonly see here in the metro in Makati City in the Philippines. Okay, and also we have here telephone wires. So telephone wires or electrical wires, okay, in different electrical fields. So that's one example of parallel lines. Okay, so parallel lines, so if we can see here the different parallel lines on the electrical wires here, okay, or telephone wires, so those are parallel lines. So other types of parallel lines can be found on different everyday stuff like books. Okay, so on books, the pages there, the edges of the pages are parallel lines. So if you really look closely on the pages of a book, so its sides there are parallel to each other. Okay, so moving forward, we have here the parallel postulate. Okay, so this is one of the 5 postulates that's been inlaid or was included in Euclid's The Elements. So the 5th postulate is actually one of the most controversial, or one of the most difficult postulates to prove it. So it's a postulate, so it's typically like a given, so it's not meant to be proven. But a lot of mathematicians and geometers during that time were discussing or debating about the truthfulness of this postulate. So it's given or stated as in a plane. Okay, so let's draw a plane here. Okay, so let's write a plane. Okay, so let's say it's plane alpha. So on plane alpha, okay, given a line, okay, let's say this is a line, let's say line B. Okay, line and a point not on it. Okay, so this is a point not on the line, so let's call it line point C. Okay, so at most there is one line parallel given to the line that can be drawn, one line parallel to the given line that can be drawn through the point. Okay, that simply means that there's only one line here on point C that we can draw that can be parallel to line B. Okay, so that's just simply it. So let's say, for example, we drew here a line. Let's call it line D. So okay, so line D, so this is the only line that's parallel to line B. Okay, we cannot draw another line here. Okay, let's say we draw here line E, and we want to conclude that line E is parallel to line B. Okay, so that's the parallel postulate that we have. Okay, so it says there, if you have one point, okay, there's only one line that can be parallel to the given line on a given plane. Okay, so it's controversial because in real world, in three-dimensional world, so this postulate kind of like bends itself. Okay, because we have these special types of geometries that has been the result of the debates and the issues that we have for this specific postulate. Okay, so we've created spherical geometry and a whole branch of geometry that we call non-Euclidean geometry, just because of the mathematicians who debated about this postulate, the parallel postulate. Okay, but for two-dimensional and Euclidean geometry, this postulate holds true. Okay, but for higher types of geometry, so it's quite a different postulate itself. Okay, so also in analytic geometry, we can see parallel and perpendicular lines. For example, we have here the coordinate planes, the rectangular coordinate planes. Okay, so again, this is kind of like a review of your linear equations during your 7th grade. Okay, for example, we have here lines A and B. So how can we say that they are parallel? So their equations must have the same slope. Okay, let's say for example, line A. Okay, so if line A has a slope of m, then line B must also essentially have a slope of m. Okay, because they're parallel. Okay, for example, line A has an equation of y is equal to 5x plus 9. Okay, so a line that can be parallel to y is equal to 5x plus 9 could be y is equal to 5x minus 4. Okay, so their slope, okay, 5, their slope are the same. Okay, so that's why they're parallel. So this is just some of the applications of parallel and perpendicular lines in different branches of geometry. And also, one of the striking features of perpendicular lines themselves, one of the things that you have discussed in your grade 7 or in your linear equations topic is that, okay, for example, we have your line C. Okay, let's say that line C, okay, has a slope of m. Okay, and if line C has a slope of m and we want a perpendicular line to line C, then the slope of the other line, or let's say line D, must be the negative reciprocal of the first line, or line C. So that's going to be 1 over negative m, or negative 1 over m. So for example, we have here our equation, is equal to y is equal to 9x plus 2. Okay, so what line can be perpendicular to y is equal to 9x plus 2? So we simply use this property that perpendicular lines are negative reciprocals of each other. So therefore, y, the line that's perpendicular to y is equal to 9x plus 2 could be 1 over 9, negative 1 over 9x minus 6. Okay, so their intercepts can be different, okay, but their slopes, okay, their slopes must be negative reciprocals of each other in order for them to be perpendicular lines. And that also holds true for parallel lines, but their slopes here have to be the same, and their intercepts can be different. Okay, so that's one of the applications of parallel and perpendicular lines in analytic geometry. And also here we're moving forward with the properties of parallel lines, which will be the main topic that we will have here in our module 2. So we won't go into detail about perpendicular lines, okay? We will go deeper on parallel lines themselves because they have beautiful properties. Okay. Before anything else, we have here the two parallel lines, as you can see, EC, line EC, and line FT. And a transversal has been drawn on those two parallel lines. We drew a transversal, we can name it GA or AG, so still the same. Okay, so a transversal, formally defined, is a line that intersects two coplanar lines at two distinct points. So this could be changed. So if there's three coplanar lines there, that's going to be three distinct points. Or we can simply say n coplanar lines at n distinct points, given that n is a positive whole number. Okay, so that's your transversal right there. Okay, and for a parallel line, for a pair of parallel lines and a transversal, it has different parts. Okay, so the first part is the alternate interior angles. So we have here the alternate interior angles for this figure. We have angle 3 and angle 5. Okay, so from the word alternate, that means they are on opposite sides. So if angle 3 is on the right, then the other angle must be on the left. So that's why it's called alternate. And interior, meaning it's inside of the parallel lines. It's in between the parallel lines. So the angles that are in between the parallel lines are angles 4, 3, 5, and 6. But since they are alternate interior angles, then we can say that angle 3 and angle 5, those pairs are alternate interior angles, and angle 4 and angle 6 are also pairs of alternate interior angles. Okay. Okay, so we've already established that. Then the other part of this figure that we have here, so this is going to be one of the general figures that we're going to have for parallel lines with transversals. We have the alternate exterior angles. So from the word alternate, again, they are on the opposite side. So if we have an angle here on the right, its alternate exterior angle must be on the left or the left-hand side of the transversal. And exterior, meaning it's not inside or in between the two parallel lines, but they're outside. Okay, exterior. So they're not inside, of course. When they're not inside, they're outside the parallel line. So we have here angles 2 and angle 8 and angle 1 and angle 7. Okay, so those are our two pairs of alternate exterior angles for this figure. And corresponding angles, from the word corresponding, so they're kind of like consecutive angles, so they follow each other. So we have here, okay, angle 1 and angle 5, so those are our corresponding angles. Angle 2 and angle 6, angle 4 and angle 8, and angle 3 and angle 7. And then we have the same side interior angles, so again, from the word interior, they are in between the two parallel lines, but same side, meaning they're both on. Both of the angles are either on the left side or the right side, so they cannot be alternate. Okay, so they're the opposite of the alternate, the same side. Okay, so we have here angle 4 and angle 5 are same side interior angles, same as with angle 3 and angle 6. And then we have, of course, the supplementary angles. So this has been discussed in our module 2 in the first quarter, if we can recall. So we have your angles 1 and angle 2. They are linear pairs, and also, of course, supplementary angles. Angles 1 and angle 2 and angle 3, angle 3 and angle 4, and angle 1 and angle 4. So if you notice a pattern, they the naming goes clockwise. Okay, so you can also go counterclockwise. Okay, so depending on your orientation there, but there you go. So you can name it from 1 2, 2 3, 3 4, or 4 1. So those are supplementary angles. Same goes with 5 6, 6 7, 7 8, and then 8 5. Or you can go counterclockwise with that one. Okay, so those are our parts for the pair of parallel lines that we have, and the transversal as well. Okay, so again, we have these theorems. Okay, the first theorem is the first theorem that we can prove here in our topic is the alternate interior angles theorem. So it basically says that if we have two parallel lines in a transversal, then the alternate interior angles are congruent. So that means angle 4 and angle 6 are congruent, and angle 3 and angle 5 are congruent, given our figure here. And also we have the alternate exterior angles. So this one works for the exterior angles. The alternate exterior angles are congruent, okay, given that we have two parallel lines in a transversal. And then their corresponding angles. So corresponding angles are congruent. Okay, so angle 1 and angle 5 are congruent, 2 and 6 are congruent, 4 and 8 are congruent, and angle 3 and angle 7 are congruent. And then lastly, we have the same side interior angles theorem. So this theorem is also one of the theorems that we're going to try to prove later. Okay, so it simply says that if we have two same side interior angles, we have a pair. So those pair of angles are supplementary. Okay, so they're not congruent, but they're supplementary. That means the sum of the measurements of angle 3 and angle 6 are 180 degrees. Okay, because they are supplementary angles. Okay, so it's very important that we try to remember these theorems. Okay, because we can use these theorems in proving higher or more complicated geometrical figures or more figures that we're going to try to look for in the future. Okay, so we have here our first proof. Okay,